In this problem, we are going to compute the mutual inductance of two solenoids. Solenoids are placed like that. One of them, this long one, is inside the bigger one. So they are placed like this. So there are some parameters in here. I have written them down. So for each solenoid, we have these three parameters. The area is the cross-sectional area in here. It's that area. Length is the length of the solenoid, the total length, and n is the number of turns, so the number of turns of wire that goes around them. So apart from that, I'm going to assume that this wire is distributed uniformly. So as a result, you can then compute the number of turns per unit length by just dividing these numbers. So in any case, we also have the same quantities for the bigger one. So I'm going to assume that my solution is going to depend on these assumptions, that the first one is longer than the second one, as shown in this figure actually. And the first one has a smaller area than the other one. So as a result, they can be positioned like that. You can also solve the problem by assuming that both the length and the areas are of the first one are smaller than the other one. It can be solved like that. There is no problem, but I suggest that you actually do it by yourself. So what is interesting in here is that I can compute the either mutual inductance M12 and M21. And in each case, of course, the calculation details are different, but at the end, we find the same quantity for both of them. So that's actually a nice illustration that shows that these two mutual inductance quantities are the same. It's just a demonstration that this is the same. So I'm going to start with I think I'm going to start with M21 in here. So that means I'm going to assume that there is a current on the wire of the first solenoid, and this produces a magnetic field, and then whatever, I'm going to compute the magnetic flux for the second one. So there are these two steps therefore. So in the first step, I'm just going to compute this, and then I pass to the other one. And then finally, I'll just compare these two. And, right, so let's just then find M21. Again, let's remember that this is basically the coefficient that appears when I express the flux in the second circuit in terms of the current in the first one. So that means I'm just going to assume that there's a current in here. So I mentioned this in the problem, in the question, that I'm going to assume that these are sufficiently long. That means that, of course, the length of the solenoid is much bigger compared to the size scale for the cross-sectional area. So if that's the case, then I can make this infinite solenoid assumption. So I can compute the magnetic field produced by the solenoid, assuming that this solenoid is infinite. But of course, I'm not going to derive the formulas now. If you remember, for an infinite solenoid, we have found this by using Ampere's law. The magnetic field inside, let me write it down like that. This is B1. This is the magnetic field produced. So it's produced by the current in one of the wires is equal to I1. So in that case, the magnetic field inside is equal to mu0 times the number of turns per unit length multiplied with the current. Mu0, we call this as little n, if you remember, when we discussed the Ampere's law. So that was the expression. So that's inside, and it is 0 outside. So there is no magnetic field outside, so outside it is the magnetic field is equal to 0. There is a uniform magnetic field inside, and the value of the magnetic field is given by that expression. Let's just remember this, because this is one of the things that we are going to use a lot. So the fact that this is also uniform is important. So that's the first step, basically. So I'm assuming that there's a current flowing in the first circuit. That current produces a magnetic flux in here. So then let's draw the second circuit. So the second circuit is like that. And of course, the first one is inside like this. So basically, there are these magnetic field lines in here. And these magnetic field lines are present only in here, within the cylinder formed by the first solenoid. So that's B1. So I can look at this picture from this point of view. In that case, the first solenoid inside would look like a small circle. Big solenoid is going to look like this big circle in here. And the magnetic field would be present only inside the small circle. Right? There's a magnetic field in here, so that's B1. I don't know what to write in here, or let me show it like that. That's B1 and show with an arrow. Right? There's a magnetic field only inside. This means the flux is present. The magnetic flux is basically crossing only that area in here. Okay, so that's going to be important, because since there is no magnetic field in this region in here, the area of that region is not going to be important. So as a result, that's basically what I need to do, is to multiply this B1 with this area in here. So that's the area A1. So I'm not multiplying this B1 with the area of the big cylinder. I'm multiplying it with the area of the small cylinder, because the magnetic field is completely inside. So there's another thing in here. It's the number of turns in the second solenoid. So there are N2 turns in there. N2 turns. So I can think of them as not as a single wire, but N2 circular wires. So that means the area, therefore, would be multiplied with N2. Right, so that's the other detail. So therefore, let me erase this part now. So as a result, I would say that the flux, therefore, over the second circuit is, first, it is multiplied with N2, because the second circuit contains N2 loops. Each loop is a circle like that goes around this magnetic field containing region. And the basic unit of flux is B1 times the area A1. Okay, so that's essentially the final expression. All we need to do now is to express everything in terms of the currents and then read the coefficient. So we already know what B1 is. It's given by this expression. So therefore, this is N2 times mu0 N1 divided by L1 I1 times A1. And unfortunately, I don't have much space left in here. So let me continue in this new page. So phi 2 is mu0 N1 N2 divided by L1 times A1. Let me come back. L1 A1 multiplied with the current. So therefore this is M21 times I1. So that means M21 is equal to mu0 times N1 N2 divided by length 1 area 1. Okay. So at this point, let's just look at and if it really makes sense. It is nice that the mutual inductance depends on the number of turns. So we have seen that if the number of turns increases, since other geometrical factors are the same, the mutual inductance should be directly proportional to the number of turns, and this is what we see. So this is quite reasonable. So mutual inductance is proportional to both number of turns. It's proportional to the area of the first solenoid and inversely proportional to the length of the first solenoid. Somehow it doesn't depend on the area of the second solenoid or its length. So as a result, it doesn't look like there could be a symmetry in here. But of course, I mean, we are going to use a different geometrical argument to compute M12 and see if we are going to get the same quantity. So let's just remember again this thing. There's actually current only on the solenoid inside, on that solenoid. And that produces a flux in the second solenoid, but of course the magnetic field is not, is only present in only part of that total area in here. So the total area of the second solenoid never enters into the argument in here. All right, so less than pass to the other thing. So let's just compute M12. Again, let's remember that this is the coefficient that appears when I express phi1 in terms of I2. So that means I need to consider this big solenoid in here. Suppose that there's a current I2 passing over it. So therefore, this is going to produce, it's just an exaggeration. It's going to produce a magnetic field B2. As I said, this is an exaggeration. Of course, normally I expect the length of this solenoid to be much larger than this side in here. But I'm just pictorially depicting the thing in here, so I don't want to, I'm not really trying to make it more realistic. So in any case, let's just say that B2 in here is going to be equal to mu0 times the number of turns divided by length multiplied with the current. So it is nice that now I have the length of the second solenoid entering into the equation. So of course it should physically appear in there. In any case, then we place the first solenoid. So the first solenoid is there. I'm going to look at it from this point of view. In that case, when I look at it, I'm going to see this picture. So the first solenoid is going to look like a circle. The second solenoid is going to look like a circle, a bigger circle. And there's magnetic field everywhere in here on the bigger one. All right, let me just bear with me. Let me draw all the dots in here. All right, so I'm bored. But of course, when I'm computing the flux through the first solenoid, of course, I need to consider only the area enclosed by this first solenoid, and it is that area. So even though the magnetic field is in a wide region now, I'm considering a smaller area. Just compare it with the previous argument in there. In any case, so I just need to multiply the magnetic field with the area A1 in here. There's another thing. It's basically an infinite solenoid assumption. So some people might think that, of course, this magnetic field continues like that. And so therefore it has the same magnetic strength. No, it is not the case. Of course, we know that there's this realistic situation where this magnetic field really continues, so, but in that case, it becomes weaker in that region. I mean, this is really what's happening. But we are making this infinite solenoid approximation in here. So in that infinite solenoid approximation, even though it looks quite unphysical, and it is unphysical, the magnetic field outside is zero. So that means it is zero also in here. So this is an outside magnetic field as well as in here. This one actually we are not that interested in, but it is that part the magnetic field is 0, so that's important. In reality, it is not, but we know that the magnetic field in that region is not as strong as the magnetic field inside. So because of this fringing effects, the magnetic field is basically going to diverge in here. So as a result, we are not going to get a very strong flux in that region. In reality, this is what's going to happen. But we are going to make this approximation that the field is exactly 0 in here. So that's one of the important things, because if I'm modeling the first solenoid as a series of circular loops in here, N1 circular loops, in that case, these circular loops do not have any flux. And so as a result, when I'm computing the total flux through the first solenoid, I have to exclude this part of that solenoid. So I'm going to look at it this time from the side view. Side view looks like this. All right, this is the side. This is the boundary in here, but let me not draw the boundaries. So what I'm saying in here, again, this is an exaggerated picture. The magnetic field is present only in here. Okay, let me just draw one more line. So what I'm saying in here is that this is the solenoid 1. So there are these circular loops of wire in here, N1 of them, N1 loops. But some of these loops do not see any flux at all. These ones do not see any flux. But the loops inside the second solenoid, they are going to see a flux. So as a result, what I need to do is to actually count the number of loops that lies inside the second solenoid. So that's basically one of the calculations. So that's the number of loops, or the number of turns which remain inside the solenoid 2, because these are the ones that are going to actually see the flux. So let me call this as N1 prime. This is quite easy actually, because I can see that, since I make this uniformity assumption, this is basically N1 times, let's see, L2 divided by L1. Right, let's remember this. L2 is the length of this outer solenoid, or the shorter one. L1 is the length of the smaller one. So I don't know how to draw this, so let me call this as L1. All right, let's just remember this. So therefore, flux through the first solenoid is equal to that number of loops multiplied with the area of each loop, which is A1, multiplied with B2. All right, so then, of course, we just combine these three relationships. So let me continue with the next page. Phi 1 is N1 prime A1 B2. N1 prime was N1 L2 over L1. This is A1. B2 was mu 0 N2 over L2 times I2. If you look at this expression, the magnetic field depended on L2, but somehow there's another L2 factor in here. So as a result, these two L2s cancel each other. So somehow the full expression doesn't depend on the length of the second solenoid. The area of the second solenoid also never enters into the argument in here. So as a result, what we get is mu 0 N1 N2 divided by L1 A1 multiplied with I2. So that's basically M1 to I2. So M1 to is also equal to mu 0 N1 N2 L1A1. And we just noticed that this is the same mutual inductance that we have found before. Right? If you don't believe me, then let me go back to that page. Yep, it's the same expression. So as a result, this is a very nice problem that illustrates that the mutual inductance is actually the same either way around. So if the outer solenoid affects the first solenoid, then the first solenoid affects the outer solenoid with the same strength. That's essentially what it means.